So somebody asked me if I thought that not taking organic chemistry would put students at a disadvantage in this part of the course, and I don't think it does. But to make sure that everybody's on the same page, I'm going to just quickly run through some acid-base stuff, in particular strong acid, strong base, weak base, some reminders about polyprotic systems and polybasic systems, and just to hopefully catch everybody up to make sure that people that have had organic chemistry more recently than not won't really you won't really suffer by that difference. So just to recap, we've already done the definitions of Ka and Kb that come from the corresponding equilibrium constants. In acid dissociation, we have Ha plus water makes H3O plus A minus, and then for base dissociation, we have base plus water makes BH plus hydroxide ion. And these are all consistent with the Bronsted definition of acid base, which is proton donor and acceptor. But so we can say that we have a base and an acid, and we get a conjugate acid that comes from the base and a conjugate base that comes from the acid. Likewise, up here, we have acid, base, conjugate acid, and conjugate base. And over here, we have the corresponding equilibrium constants. Ka has H3O plus A minus over Ha, and Kb has Ha OH minus over A minus, all of which come straight from here. We put the numerator is the products of the reaction, the denominator is the reactants in the reaction, and we don't include water because that's a solvent. And we would say that when Ka is big or when Kb is big, we have a strong acid or a strong base. Otherwise, in most cases, we have weak ones. So here's some that you should know. The strong acids, HCl, HBr, Hi, sulfuric, nitric, and perchloric acids are all strong. That is to say they dissociate 100%. So we have Ha plus water makes H3O plus A minus, and this is a 100% reaction, essentially. Now, there is one thing on this list. There's sulfuric acid. Sulfuric acid is a diprotic acid, and so strictly speaking, the product H2SO4 makes HSO4 minus. Now, that's also an acid. It can dissociate again to form H plus and SO4 2 minus, but it turns out the equilibrium constant for this is much smaller, around 10 to the minus second. So we don't see as much dissociation from sulfuric acid after the first proton is dissociated. So these are the ones you should know. For bases, you should know lithium, sodium, potassium, rubidium, cesium, hydroxide are all strong bases because essentially they generate 100% of the corresponding hydroxide. Now, there are some not particularly strong hydroxides, and so things like some insoluble metal hydroxides that don't tend to dissolve or don't tend to ionize, but that doesn't apply here. And the last one is a quaternary ammonium, where you have a nitrogen with 4 groups bound to it, and this will have a plus charge, a plus formal charge on the nitrogen center. And so really there's no place for a hydroxide ion to go. There's nothing for it to bond to on the ammonium side. So there's no reverse reaction that can take place. And so that's why this reaction leads to the formation of a high concentration of hydroxide, making quaternary ammonium hydroxide a very strong base. So you should know these. They sort of constitute the currency of chemistry, and we'll see common examples of them later on. Outside this, I would say that any acids that you encounter, unless otherwise specified, we could say are probably weak. And they'd certainly be weak if you see, if I report a sufficiently low Ka. So weak acids and bases only partially ionize, and there's a couple common ones. Carboxylic acids are weak acids. Metal cations form weak acids, and they're conjugates. So carboxylic acids, their conjugates are carboxylates, are CO2 minus, and amines, their conjugates are ammonium ions. So carboxylic acids are weak acids, amines are weak bases. Also, they're conjugates. Carboxylate and ammonium salts tend to be weak as well. So carboxylates are weak bases and ammonium salts are weak acids. Metal cations like nickel with 6 waters is a relatively weak acid because it forms hexaquanickel monohydroxide plus H3O plus. And then remember that this is always true. Ka times Kb equals Kw. Not just any Ka, not just any Kb. These have to be conjugate pairs. So if you know the Ka, for example, AHA, then you can figure out the Kb of A minus if you happen to know that Kw is 10 to the minus 14th, which, well, it is. But so the good thing about this is we can always work out Kas or Kbs for the complements, the conjugates of the acidic or basic species that we already know. And one sort of big rule of thumb is that strong acids have weak conjugate bases and weak acids have relatively strong conjugate bases. So by example, methane is a really, really weak acid. And I say it's weak because it has a pK of 70. That means that Ka for methane is 10 to the minus 70th. So it's pretty small, as you might imagine. That means that, so here's the acid-base reaction, CH4 plus water makes CH3 minus plus H3O plus. This is a very, very weak acid, and therefore we can say something about its conjugate. This must be a relatively strong base. In fact, it's a really, really strong base. I think the Kb is in the neighborhood of 10 to the 86th, something like that. Kb is around 10 to the 86th power, 86th. So methane is a weak acid, correspondingly CH3 minus is a very strong base. But on the other hand, here's a strong acid. HCl is really strong, and it reacts with water to form Cl minus plus H3O plus. And here's a conjugate acid-base pair. HCl is the acid, chloride ion is the conjugate base. Since HCl is strong, we can say that we know that Cl minus must be weak. And again, judging from the pKa, we can say the pKa of pKb of Cl minus is going to be in the neighborhood of 23 or so, and that means that Kb is going to be 10 to the minus 23rd. So really, really weak base because the acid is correspondingly very, very strong. So again, there are a variety of neutral weak acids, and carboxylic acid is one. This is acetic acid, and you'll often see it written as HC2H3O2. That's perfectly fine if you remember that. I prefer to think of it in terms of its carboxylic acid structure that has a methyl group and a CO2H group. And then nitrous acid has a formula HNO2, but that might be a little bit deceptive. It's really HONO because the conjugate base of nitrous acid is ONO, the nitrite ion. And another weak acid are a family of charged ions that come from conjugate acids of amines. So ammonia reacts with acid to make ammonium ion. It's a relatively weak acid. Likewise, trimethylammonium reacts with protons to form trimethylammonium ion, and it's also a weak acid. For the conjugate bases of weak acids, we know that they're also basic. So the conjugate base of acetic acid, sodium acetate, is basic. The conjugate base of phthalic acid, the phthalate ion, is a weak base. And then any amines are weak bases, as we already mentioned. For polyprotics, remember that a polyprotic acid is one where the product of the first dissociation is also acidic, and in some cases the product of that dissociation is also acidic. So phosphoric acid is a good example. It has a total of 3 ionizable protons. I'll just draw the structure up here. There's 3 OH groups and 1 phosphorus double bond O. H3PO4 dissociates to form H2PO4 minus. K1 is about 10 to the minus third. H2PO4 minus, which is the conjugate base of phosphoric acid, is also acidic, and it makes HPO4 minus. That has a Ka of around 10 to the minus 8th, about 5 orders of magnitude weaker acid. But we don't stop there. HPO4 minus is also acidic, and it forms phosphate ion, and the Ka of that is again another 5 orders of magnitude lower. For polybasics, we can work the other way. Phosphate ion reacts with protons to form HPO4 minus. That's the same one we had up here. HPO4 minus reacts with protons to form H2PO4 minus. That's the same one we had over here. And H2PO4 minus reacts with protons to form H3PO4. And so we can relate K1, K2, and K3 to KB1, KB2, and KB3. And since the product of the first dissociation here is the one in the bottom, we would say that, let's see, it's right here. H3PO4 dissociates to form H2PO4 minus, but also in a separate step, H2PO4 minus reacts with protons to form H3PO4. And so just crossing out the things we can, let's see, we get rid of H2PO4, we get rid of H3PO4, and we have an expression for Kw. And so that means that K1, the acid dissociation constant for phosphoric acid, times Kb3, the base reaction, the base equilibrium for H2PO4 minus, multiplied together gives you Kw. So we can always work out one of these dissociation constants from the other one. And then here's a couple quick examples. Let's say we know the Ka of acetic acid is 1.75 times 10 to the minus fifth. We want to find the Kb for the acetate ion. That's a very straightforward process. We know Ka times Kb equals Kw, where these two are conjugates. And so this means that since we want to find Kb equals Kw over Ka, and look, we've already got that right there. So we can find Kb for the acetate ion. We can work the reverse kind of process. We know Kb for methylamine is that. Let's find Ka for methylammonium ion. Again, we have Ka times Kb equals Kw, so therefore Ka is equal to Kw over Kb, or about 10 to the minus 11th. And, organic chemists do have a pretty concise way of representing carboxylic acids and organic structures in general. Here's a very complicated, relatively complicated molecule. There's a benzene ring, a C6H6 ring, and there's 6 groups bound to it. In general, we don't include protons that don't have any sort of chemical consequence. So in a discussion of acid-base behavior, and I guess the rule is, if the functional group has protons in it and it's something other than a CH bond, then it might be potentially interesting. We draw in the hydrogens. So we would simplify the structure and say, well, we have a benzene ring over here, and we have some hydroxide groups there, and we have a carbon here, and a carbon there, and a carbon here. So we include some of those, but we try to minimize the excess hydrogens that we would try to draw. And so that's why we don't see hydrogens at all these vertices. We just assume that every carbon, as shown, has a total of 4 things bound to it. And if we specify what those things are, then the difference is going to be things like hydrogen. And so we'll do a quick drawing. Acetic acid, again, has a structure where there's carbons added or attached to a COOH group. And just to make it all work, we have 3 groups bound here, and those turn out to be hydrogens. It's a carboxylic acid like any other carboxylic acid because it has this common CO2H group. Actually all carboxylic acids have that structure. HNO2 is one I've already drawn. HONO. The product of this reaction after deprotonation is the nitrite ion, ONO-. which we can draw as one of two resonance structures. I'm going to draw it bent because I know there's a lone pair on the nitrite nitrogen. And of course, there's two resonance structures here we could draw that has an O nitrogen double bond here and an NO single bond here. And then finally, I've drawn this one already, but so we have H, O, P, O, OH, OH. This undergoes deprotonation to form O minus P double bond O, and then two hydroxides. And now, of course, this lone pair can be delocalized through the phosphorus oxygen, making another resonance structure. But we don't stop there. Another deprotonation forms OP, O, O minus, OH, where we can delocalize the other two minus charges through the phosphorus oxygen. And the third one is just PO4, which has this structure, where once again we can delocalize all the minus charges through the phosphate PO bond. So there's a brief survey of weak acids and bases. We reviewed things like Ka times Kb equals Kw. We looked at some general trends, the fact that weak acids include carboxylic acids and metal salts and ammonium salts that are derived from amines. We looked at weak bases, which include carboxylates and amines. And then we looked at some polyprotic systems and the fact that you can find Ka or Kb given knowledge of the Ka or Kb of the conjugate. Thank you.